Okay, maybe my setting is not right. I couldn't see you. No, no issue.
Yes, ma'am. We are live and I have started the recording.
Okay, so participants, so now we are going to start our second talk of the day. Our second speaker is Dr. P. Senthil Kumar. He is an assistant professor in Department of Physics and Astrophysics, University of Delhi. It's my pleasant duty to introduce him to the participants. So Dr. P. Senthil Kumar completed his PhD degree from Central University of Hyderabad in the year 2003 in the field of experimental condensed matter physics. After several postdoctoral research work, he joined the Department of Physics and Astrophysics, University of Delhi in the year 2008 and continues till date. He has 15 years of research and teaching experience and has taught courses like quantum mechanics, advanced solid state theory, laser and spectroscopy, etc. He has started the experimental plasmonics group and 5 PhD students have graduated from this group. He has more than 60 research publications in international journals and is one of the most cited researchers in the field of plasmonics. His name has been included in Marcus Who is Who in the World in 2014 31st edition. So Dr. Senthil, you're most welcome. And I'm sure the students are going to benefit a lot from your expertise on the subject. So I request you to kindly start your presentation.
Thank you, ma'am. Thank you. So let me share my screen.
Yeah, please.
Okay. No. Can you see my screen? No?
Not yet.
No.
No, ma'am. No, sir.
Yeah, now you have shared your screen. If you could make it full screen.
Yes. Okay. Is it visible now, right?
Yeah, it is visible.
The screen is
Now,
visible.
yeah.
Yes,
Now
sir. It is visible.
Yeah.
It is full screen now. Thank you.
Okay. Good evening, everyone. Okay, so we will continue with our discussion from yesterday. Okay, on the vibrational properties of the lattice. So before that, if there are any queries from yesterday's lecture, you are free to ask. Okay. Are there any queries from yesterday's lecture? Okay, so let me just quickly go through what we have seen yesterday, right? And then if there are any questions, you can feel free to ask. Okay, so we started with Einstein's model for the heat capacity, right? To how what Einstein proposed to explain the heat capacity of solids, right? So as to modify the Dulong and Petit's law, right? So he considered atoms to be made of small oscillators, right? Which he borrowed the idea from Planck. That's what we have seen yesterday. So we can define the energy of the total energy of the solid, right, by this equation. Okay, and we have total energy per mole we have derived, and so heat capacity is defined by the derivative with respect to temperature of the total energy per mole, right? And that's what comes out to be 3R. So that's what is Dulong-Petit's law. At very high temperatures, this is valid. But the only problem is the same law is not valid at low temperatures. Okay, that's what puzzling people. Why the law is not valid for low temperatures. High temperatures, it is like it goes to the constant 3R. That is valid even in Dulong and Petit's law. But the low temperature was the problem. Okay, so that's where Einstein proposed this model and find out the specific heat of the solids, right? Using simple classical Boltzmann equation, right? Find the average energy of the total energy of the solid, right? This is what we have seen using Planck's equation, and define this equation by this way, this method, right? These are all we have seen. So the total energy of the solid, yes, and finally the heat capacity, right? So this is we have seen yesterday. So the quantity Einstein temperature is defined, which is theta e h cross omega by k, which has a dimension of temperature. So it's rightly called as Einstein temperature. Okay. So, and this is what the equation for specific heat proposed by Einstein. Okay. Again, this Einstein's proposal also gives at high temperature the value 3R perfectly gives high temperature value, but again still the high temperature value is fine, okay, perfectly fine, but low temperature even though it the behavior is same, but it does not exactly match with the experimental data. Okay, again the behavior of the curve is similar, but not exactly matching with, as you can see here, high temperature, it matches exactly with the experimental data. The line is the theoretical data and dots are the experimental data. So experimental data matches with the theoretical data at high temperatures, but at low temperatures, even though the behavior is similar, but they are not matching. There is a small deviation. Okay, so again, so that's where the drawback of Einstein's proposal. Okay, even though it explains very well at high temperatures, low temperatures still there is a problem, similar to Dulong and Petit's law. Okay, so that's where Einstein proposed this model in 1907, and after 5 years of his theory, Debye model came into existence. So Debye is another famous scientist. Like you might have studied in crystal structures and diffraction, the Debye temperature, right? The anormalicity of the lattice is given by the Debye temperature, right? The same Debye. So he's a very famous scientist at that time. Okay, so he proposed some modifications. Okay, in the Einstein's model. So these are the two proposals he has made. So that's what we are going to see. So the Debye model of the solid, which we have seen yesterday. So it has in a three-dimensional solid, three and normal modes of oscillations are possible. The atoms can oscillate in 3 dimensions, right? That's what, and the spectrum they can oscillate with the frequency from omega to omega max in a continuous manner. Unlike Einstein's case, the oscillation frequency oscillations of each oscillator is discrete. Okay, that's why if you remember, the Einstein's equation always uses summation. Okay, so there were discrete frequencies were considered. but the modification by Debye says that it has a continuous range of frequencies from omega, from 0 to omega maximum, right? So because the atoms are considered as a continuous, the solid is considered as a continuous elastic medium. Okay, so these are the this is a simple modification proposed by Debye to the Einstein's theory. So that's what how this effectively changes the theory. That's what we were started seeing, right? So from this, he started proposing the equation for specific heat. So now the device equation for specific heat contains the integration, which means all frequency is continuous from range of frequencies from omega equal to 0 to omega equal to omega maximum, right? It's a continuous frequency. So that is the modification Debye proposed. So the whereas this n omega is the number of oscillators per unit omega. Okay, different. What is the range of oscillators having different energies or different frequencies, right? And this one is a same Einstein term, right? Total energy term. So this is a modification proposed by Debye. Okay? So we will see how it works in this case. Okay, so yes, but since he is considered as a continuous elastic medium, also one-dimensional one, he can propose a wave equation, right? For the wave propagating along the, say, if you consider one dimension along the x direction, the same it can be extended to 3 dimensions like x, y, z direction. So for simplification, we can do it in 1 dimension and then extend the results to 3 dimensions, right? That's what Debye has done. So so the one-dimensional wave equation is written like this, and so from that we can find that the speed of wave speed is independent of the wavelength of the medium, elastic medium, which is solid here, right? So then you can find the orbit frequency omega, right? The relation between omega versus k in terms of wave vector k is called the dispersion relation, right? So the any relation in general between omega and k, right, is a dispersion relation. So here the dispersion for one-dimensional wave equation, the dispersion relation is just linear. So there is no dispersion as such in the one-dimensional wave equation, right? So, so from one dimension, this relation, you can find out the group elasticity. So, what do you mean by group elasticity? Group elasticity, how the energy is transported from one end of the solid to the other end, right? So, the atoms does not physically move, but they transport their energy, right? That's what is given by this equation. So, the group elasticity corresponds to the energy transportation in the solid, right, without the physical movement of the atoms as such. Okay, so that is what is given by this group elasticity. Okay, so now we will see an extension of this idea in the one-dimensional monatomic lattice. Suppose we consider a one-dimensional lattice or with consists of n number of atoms, right, in a one-dimensional chain. So we have, as proposed by Debye, these atoms can have atoms are vibrating about their mean positions, and they can be considered as small atomic oscillators, right? So in a one-dimensional chain, the atoms are vibrating around their mean position. So that that is considered as a small atomic oscillator. And let's try to find the dispersion relation for this one-dimensional chain, right? Using a device model, basically, right? So for if you consider a particular atom, yes, in the one-dimensional chain, right, the force acting on the chain and this atom, right? There, as it's a one-dimensional chain, there is a force acting from left side or from right side, okay, between its nearest neighbor only. Either a force can act from s minus 1th atom or s plus 1th atom on yes, right? So that is a force acting on the S atom, on one particular S atom, right? So the force acting on the atom can be written like this: summation over all p's, where p's are the nearest neighbors. Either for S, it will be S plus 1 or S minus 1, both from left side or right side, right? And okay, this is what is the force U of S plus P, means either S plus P or S minus P, either from right side or from left side, and acting on US, right? And the CP is the okay, something like a spring constant, right? K, which you generally refer. So here it is represented by the C because of their displacement. So that's why CP, the P refers to interactions from minus infinity to plus infinity, right? Because both sides it's same only, right? Because it's a one-dimensional chain, right? So you can write this one as equating it to Newton's second law, force acting on a particular atom, right? Mass into acceleration, which is famous Newton's second law. So you can equate this force, right, to mass into acceleration, right? And since it is a simple one-dimensional wave equation, we can apply a plane wave solution, right? Substituting a plane wave solution for the displacement of the atoms, US is exponential IKS minus omega t. We can substitute for US in this equation, force equation, and simplify. So if you equate the like terms, okay, you will get a relation between omega and k, okay, because you are substituting a planar wave solution. So simplifying that equation, you will get relation between omega and k, right? See here, it is a summation over all p's, which is minus p to plus p, which is minus infinity to plus infinity. But since both sides, all atoms are same monatomic lattice, all atoms are similar. So you can consider, if you consider, say, this is summation over p here, you see. So it is considering both sides interaction. So instead of that, because both all are similar one, so instead of doing both minus infinity to plus infinity, you can simplify that. You consider only one side, the right side or left side, and multiply by 2, right? So then it will be simplified. So that's what is here. It is given finally that p greater than 0, but there is a factor of 2, right? Because whatever happens on the right side, it is same as left side. So that's why the summation symbol is changed, p greater than 0 always, right? And the factor of 2 is added here. Okay, so it is same as this previous equation where p is over all minus infinity to plus infinity, but here only it is p is greater than 0 to infinity. So there is a factor of 2 is added here. Okay, that's all. And so you get finally, after simplifying, you get relation between omega and k, right? So that is a dispersion relation for a one-dimensional monatomic lattice. Okay. So, okay, this is what we have seen yesterday. So we can, as you can see, this omega versus k is periodic in terms of k. So k minus pi by a to plus pi by a, it is periodic, it extends. And okay, so after that, it is again periodic, right? 0 to pi by a, it extends to pi by a to 2 pi by a, 3 pi by a. So it periodically extends, okay? But its range is from minus pi by a to, the total range of k is minus pi by a to plus pi by a. So which corresponds to the first Boolean zone, right? So if you consider only one Boolean zone, you can extend that to the whole solid itself. Okay, that's a whole idea. So that's what this range of k implies. Okay, so what happens when k is bigger than this one? Let's suppose if k is bigger than a, is either plus pi by a or minus pi by a. What happens? Okay. Obviously, when k is equal to plus or minus pi by a, the group velocity is 0 because the energy cannot be transmitted, because the energy cannot be transmitted outside the solid, right? The energy from one end of the solid to the other end only, but outside the solid, the energy cannot be transmitted. So that's why it is 0, because this equation, as you can see, this equation involves sine square Ka, right? So, which is R exponential Ika, right? So we can write it cos pi plus I sin pi, right? Which is when you put pi by A, it becomes -1. Okay. So each neighboring atom at 180 degree out of phase. So they cannot interact. So when they are not interacting, then the energy cannot be transmitted, right? So that is the idea. So that is why there is a restriction on K, which is say plus or minus pi by A. So above this value, so that's why this where this energy dispersion relation, okay, it's abrupt at this K at this end, okay, at this end points, pi by A or minus pi by A, it abruptly ends, okay. Then okay, plus minus pi by A to minus 2 pi by A, it again starts the same way, right? Periodically it extends, okay. So that is a limitation on K, and it is also valid because this is a physically valid one, because outside the solid the energy cannot be transmitted, right? And this region plus pi by A to minus pi by A is the first value of the one-dimensional lattice. So the same idea can be extended to three-dimensional solids also, right? So once you know about one dimension, it is easy to extend it to the same idea to three-dimensional solids. Okay. Only thing is the equation becomes three dimensions, so it is more rigorous to compute them, but nevertheless the ideas are the same, right? So okay, so that's why. So to summarize, this is a phase velocity. Phase velocity means each individual atom, how they are, what is their energy, individual energy, what is the force acting on them, each individual atom. But group velocity is a combination of the whole collectively, right? So that how energy is transmitted, right? So the group velocity tells you about the energy transmission inside the solid, okay? So that is what the physical implication of group velocity, okay? And for a small k, okay, in the limit small k, this group velocity becomes phase velocity, right? So in the limit small k, we call this as acoustic vibration modes, acoustic modes, because this at the small k limit, the energy of this group velocity or phase velocity is equal to the speed of sound, okay? So sound frequency. So what is the sound frequency? This 2 hertz to 20 kilohertz, right? The sound frequency. So that is a range of this velocity in the small k limit. So that's why it's called just because of its equivalence of energy, right? From 2 kilohertz to 20 kilohertz, right? That's the speed of sound. So that's why it's called acoustic mode. Just for the energy range lies in the acoustic speed of sound, so it is called acoustic vibrational mode. Okay, so this is about for one-dimensional monatomic lattice. Okay, suppose if you consider, but in normal in solids like so if you consider NaCl or multi-compounds, right? In a unit cell, there are many atoms, right? Many different atoms. So the simplest possible example is that if you consider a diatomic lattice, okay, one-dimensional diatomic lattice, where say mass small m and capital M are there. So just a simplified model, okay. So this shows that atoms can have different atoms in the unit cell. So if you can, yeah, one-dimensional atom, sorry, one-dimensional diatomic lattice with two masses, small m and capital M, and do the same similar thing, force acting on individual atoms, right? And write the force equation and equate it to the Newton's second law, right? Force, mass into acceleration, and implement a plane wave solution like one-dimensional. So you can have a solution, plane wave solution, and insert the solution for US, right? And do the same thing as before for one-dimensional monatomic lattice. So you will get a relation between omega and k. But very interestingly, for this one-dimensional diatomic lattice, instead of one peak, you get two peaks with a small gap in between them, right? So when you solve the wave equation for one-dimensional diatomic lattice, you will, as in the similar way for one-dimensional monatomic lattice, you get two vibrational modes, okay, two branches of vibrations. One is in the energy range acoustic, speed of sound range, and another one is in the optic range, optic branch. Optic branch means in the electromagnetic visible spectrum, right? So the energy range is here around 2 to 4 electron volts. Here it is very low, much low compared with this optic branch. So the optic branch always has a higher energy than acoustic branch. So based on their energies only, so they are called as they are synonymically named as, say, acoustic branch and optic branch. Acoustic branch corresponds to speed of sound, and optic branch corresponds to the visible electromagnetic spectrum range, right? Visible, simple visible light range, which is 2 to 4 electron volt range, right? So a simple one-dimensional diatomic lattice contains two branches, okay? So again, this same thing can be extended to 3-dimension also. So in 3-dimension, in the unit cell, suppose if unit cell contains two different atoms, right? Then there are two vibrational modes possible. You can straight away say that there are acoustic modes and optic modes possible in that solid, right? With multiple atoms in the unit cell. So this is a so simple classical, even though classical theory, it explains very well, and this is valid for all the materials, okay? So no matter whether it's a old material, known material or unknown material, this vibrational property is excellently valid for all the materials, okay, known till now. So, okay, in summary of this, so acoustic modes, so atoms move in. So if you see this one, acoustic modes, atoms move in phase with each other. All the atoms are moving in phase with each other. That's why their energy is, when all the atoms are in phase, their energy is minimized. So obviously the energy is low. That's why it's called in the lies in the speed of sound range. So it's called acoustic mode. So remember that when you say acoustic modes, it is implied that atoms move in phase, same direction. All the atoms move in the same direction at the same time, right? So that is what is acoustic modes. And optical modes, atoms move anti-phase because they are having higher energy. So because since different atoms have different phases, so to move, they need a higher energy. So when they are in out of phase, means anti-phase, it's not out of phase. Out of phase is the extreme condition. K is plus or minus pi by A, right? But within the K range, they are out of phase. Okay, within the minus pi by A to plus pi by A range, they are different atoms are having different phases. So they need higher energy to oscillate, right? So that's what they are called optical modes. Okay, so optical modes always have higher energy, right? So this is a simple definition. This you should always give when any problem or any this discussion. If it is mentioned as acoustic modes, you have to it automatically implies that atoms move in phase with each other. Okay, whereas optical modes means atoms are anti-phase, okay, or slightly out of phase with each other, but within the K limit. Okay, K means plus pi by A to minus pi by A limit. Okay, so acoustic modes always have lower energy, optic modes always have higher energy. The name itself implies that which one is having higher acoustic modes lower energy, optic modes higher energy. Okay, so just remember this so this is a summary of omega versus K is called dispersion curves, right? If you have n atoms in the primitive cell or unit cell, you will have 3n branches. Okay, in summary, you can call it as if there are n atoms in a unit cell, right? That atom has 3n vibrational branches. Okay, so in this 3n, what are the acoustic and what are the optic branches? So there will be for 3n branches, a total 3n branches, right? If there, say, suppose if there are two atoms, like in a diatomic lattice, there are two atoms, so 3 into n, 6 branches. So in 6 branches, 3 will be acoustic, okay, means with the speed of sound, and remaining 3n minus 3 will be Arctic branches. Okay, so which means that there are 3 in a atom with 2 unit cells, two atoms in a unit cell in a solid, right? You will have 6 branches, 3 acoustic and 3 Arctic branches. Okay, so this is a overall summary. So this is valid for any solid. So depending on how many n atoms present in a unit cell means 3n branches, and of them 3 will be acoustic branches, because say atoms have to move in phase, so which is not always possible. So there will be only less number of acoustic modes than optical modes, because atoms, when they can move in random, so they prefer to move in random. So that's why more optic means 3n minus 3 optic branches. There will be always more optic branches than our acoustic branches. So acoustic branches will be only 3 in a n atom cell. Okay, but whereas 3n minus 3 optic branches. Okay, so this is valid for all atoms. So this you keep it. This is an overall summary, right? You can keep this in mind, and this is valid for all the solids. Okay. Even though Debye's theory was 1912, at that time even quantum mechanics was not there, right? But even then, his theory explains beautifully that the number of acoustic and optic branches in solid. Okay, so this summarizes the vibrational properties of the lattice. Okay, so the dispersion relation. It matches with the experimental data very well. Okay, so even though the device, even though it's a classical description, it matches with the experimental data very beautifully. Okay, that's the idea. So now we come back. Okay, this was a distraction. Using device proposal, okay, we can find the optical modes and acoustic vibrational modes in solid. Right now, but our aim was to find the specific heat capacity, right? CV, specific heat capacity at constant volume, right? So based on a device proposal, okay, we have to now count how many number of frequencies possible. He proposed that all frequencies from omega equal to 0 to omega maximum is possible. So what are those now? What is omega maximum, right? We have to find out. He proposed it cannot be an arbitrary quantity for a given solid, right? So depending on its electronic configuration, right, it has to have some cutoff value, like omega maximum should have some value. It cannot have some arbitrary value. Okay, so that is what even Debye proposed very beautifully how to calculate that. Okay, so he used a very simple method. Okay, so how to calculate that? So a vibrational mode is given by wave vector k. So the wave vector k, so as you can, as you know, the wave vector k is a dimension of 1 by L or 1 by lambda, right? 1 by wavelength is wave vector, right? So that relation, you know. So and energy is E h cross omega. Okay, E equal to h cross omega. So now how many modes are possible? That's what Debye asked in, say, between energy range omega E k and omega plus d omega. Right? So what is the number of modes, vibrational modes possible within this small, say, omega and omega plus d omega range? Okay, so if you know that, we can expand the same thing to the entire solid and find the omega maximum. What is omega maximum, right? So we slice the solid into different energy ranges and find each and integrate over the entire range. So we get what is the maximum range of omega maximum possible in a given solid. So that's what Debye proposed in a very methodical manner. Okay, so suppose if there are number of modes in the range n omega d omega, so we can have over the entire volume, right? D cube k. So that's what. Let us see how he has systematically calculated, so that once you know this omega maximum, we can substitute in that specific heat equation and integrate. You can get the specific heat of the solid, right? So that is a idea. So for that we need, okay, what is the boundary? Suppose if we consider one-dimensional chain, right? So what are the boundary conditions? What is the boundary condition? So fixed so that we can find the energy range within that boundary condition, right? So this was very essential. So how to propose boundary conditions for a one-dimensional chain? Okay, because it extends from minus infinity to plus infinity, right? One-dimensional chain, long chain, right? So what are the periodic boundary conditions? Okay, means how to propose a boundary condition for that. See, as you can see here, it's a one-dimensional chain of atoms, right? Each atom are equally placed, of course, right? So suppose if you consider this atom, the position of this atom is SA, and this nth atom is S plus N A. So what is the relation between this atom and this atom? Because they are situated in a long one-dimensional chain. So there is a proposal, periodic boundary condition proposal by these two famous mathematicians like Born, von Karman. You know this Max Born, right? You know the optics book, who has written the book on optics, right? So Max Born is and von Karman, right? It's a famous mathematician. So these two has proposed a boundary condition in a very, very intuitive manner. So since it is a one-dimensional long chain, right? So suppose if you connect these two ends, this and this two ends, right? They form a circle. Okay, so like this. Okay, these two atoms, with two end atoms of one-dimensional chain, you connect them, right? So then you will find that it is periodically repeating, right? So yes, yes plus one, yes plus two, and go to yes n minus one, and again yes, and it comes back, right? It keeps on repeating. Okay, the same thing was happening from minus in the one-dimensional chain. It keeps on happening in two directions, right? Now, intuitively, what they have done is they just connected it to form a circle, okay, and find that it is periodically oscillating, right? It keeps on coming back, right? So that's how. So we assume that the lattice has a similar behavior, right? Because inside the solid, it has to be keeps on repeating, right? So that's what. So this simple intuitive formulation, okay, gives you a set of boundary conditions, okay. So that is what is proposed here. Since the atoms S and S plus one, right, as you can see here, previous one, S and S plus N, right, have the same displacement, because all atoms in a one-dimensional, all atoms have the same, all are similar atoms, so all are having the same displacement. So since both S and S plus one have the same displacement, we can write it as the displacement of S atom is equal to the displacement of S plus N atom, right? So again, that is what is given by this periodic boundary, circular boundary conditions, okay, which are actually mathematically proposed by Born, von Karman, okay. And Debye, okay, use those mathematical idea in the physical, like solids, okay. And so that is a very very knowledgeable. Debye has correlated the two, okay. So that is what, that's why he's a rigorous, which a methodical theoretician, right? Debye was very famous even at the 1912, okay. So you have to appreciate his intuitiveness, okay. So since both S atom and S plus N atom has similar displacement, then we can equate the plane wave solutions, right, of the S atom and S plus N atom. Okay, so if you equate them, so you will get the solution as say e power I k n a is equal to 1, right? That's what you will get. If you cancel the like terms, you will get 1 equal to e power I k. So from this, you know what are the allowed values of k, right? So k is 2 pi n small, 2 pi n is a small number, and n, right? So these are the limitation or allowed values for k, right? The wave vector, which is of the dimension 1 by L or 1 by wavelength, right? So by simple this boundary condition, right? Displacement of the S atom is equal to the displacement of the S plus nth atom. We get the allowed values for k, right? So now the separation between the allowed solutions. So separation between two k values, right? Is del k, right? K1 and K2, right? Two nearest neighbor atom, if you see, and subtract them, which gives you del K. So del K is 2 pi by Na, where N is the total number of atoms in the, say, one-dimensional chain, right? So which is again independent of K, right? And these are called the density of modes, right? In the K space is uniform, right? That's what, so the density of modes in the K space is uniform because it is independent of K, right? The separation between two K values is independent of K. So the density of modes is uniform. So in the range omega, whatever range, omega plus d omega, if you consider that number, density of modes is uniform in the K space, right? So that's what this implies. So just this simple K value, allowed K, from the allowed K values, we calculated the separation between the two K1 and K2, right? Which gives you, which is independent of K, which shows that the density of modes are constant in a given K space of the solid, right? So we can find the number of modes divided by the interval of K space, okay? So 1 by del K, right? So what is a mode? What is a range of energy for one particular mode, okay? So in one dimension. So this is in one dimension. So we are considering one dimension chain. So the density of modes in one dimension chain is L by 2y. So it depends on the length of the chain, okay, by 2 pi, okay? So this is what 1 by del K is given by this equation, okay? So, sorry. Okay. So this is what, this will give you the density of modes in that particular energy range, omega plus d omega, okay? So in the one-dimensional chain, we have, say, 0 to n atoms, right? Carrying total length is L, the chain total length is L. And so if you fix the position of the atom 0 to m, if there are m atoms, you can have, each of them have a vibrational mode, right? Which is given by this formula, which you know from the previous discussion, right? Xn, we can calculate. So we can calculate the allowed values of K, which as before. So the allowed values of K are given by this equation, right? K is pi by L, 2 pi by L, and things like that. So as you can see here, the 0 K m pi, K equal to m pi by L is not allowed because the end atom cannot vibrate on both sides, right? Because say, suppose if we consider this as the end of the atom, end of the solid, right? So this nth atom cannot vibrate both sides uniformly, right? So that's why always it starts from say 1 to m minus 1, okay? So the 0 and m, the end atoms are not considered because they cannot vibrate uniformly, okay? So that's why the edge values are not allowed, okay? Because at the edge it is always 0, okay? So that's always 1 to m minus 1 considered for as far as the vibrations are considered. So that's why there is a limitation on the allowed values of K, right? So these are the only allowed values of K. K is pi by L, 2 pi by L to m minus 1 by L pi, right? So these are the allowed values, okay? So from a simple classical description, we can find the allowed values of K, right? So yeah, we have m minus 1 allowed independent values of K. So, okay, so these are the same number of, so 1 to m particle, m minus 1 particle only are allowed to move. The edge ones are not allowed to move because they cannot move uniformly on both sides, right? So in K space, we have this m minus 1 allowed wave vectors, okay? So in a one-dimensional chain, only if there are m atoms, only m minus 1 modes are available, right? Wave vectors are possible. Rest of them is not possible. Okay, so dk by dn is the pi by l is the number of n is the number of modes. Okay, so this is in the k space, which is k space means Fourier space are in the Boolean zone, right? In the pi by a, only this much number of modes are possible. Okay, discrete number of modes are possible. So similarly, so once you know the number of modes in one Boolean zone pi by a, so we can using that we can calculate whatever range. It means in different regions what are the possible allowed values of k, right? So density of states, which are called density of states, okay, the number of allowed modes of k gives the number of modes per unit frequency per unit volume, right, of the what is the Fourier space, right, which is given in one dimension like this, right, which is okay, which is simply the group velocity, right? In one dimension, it is 1 by pi 1 by t omega by dk or dk by d omega, right? So it is simply the inverse of group velocity. So there is no singularity at pi. So at k equal to pi by a, there is a singularity. So it cannot move beyond, go beyond pi by a, right? So that is the idea. So that's where this periodic boundary conditions, right? As we have seen, von Karman periodic boundary conditions simplify. Okay, it's using that it is very easy to find what the allowed values of k, and using that what are the density of states possible, means the number of modes having a particular energy in per unit frequency range per unit volume, right? So that is what we can call, basically the density of states. We can, density of states means the number of states having a particular energy per unit frequency per unit volume, right? So that's what we can calculate, which is given by this del k is 2 pi by L. Okay? So that is what in one dimension. So this the same thing can be extended to higher dimension, 2 dimension or 3 dimension, right? So in one dimension, it is a chain. Okay, one dimension chain. Suppose if you go to 2 dimension, in k space, it will be a circle, right? The different k space possible. So it is a circle. So it when it is a circle, it is the density of states is given by the same area of the circle, right? D omega is given by the group velocity, inverse of group velocity, which means the L by 2 pi whole square, right? Which is area of the circle, right? So that is what in 2 dimensions, right? In 3 dimensions, you can see it is per unit volume, right? Because x, y, z volume, right? So in 1 dimension, it is length. In 2 dimension, it is area of the circle. In 3 dimension, it is volume of the sphere, right? So when you consider the volume of the sphere, it is L by 2 pi whole cube, right? The density of state, 3 dimension density of state will become 1 by the group velocity. So which is L by 2 pi whole cube, right? Or 2 pi by L del k is given by this 2 pi by L whole cube, right? So these are the, so from one dimension it is 2 pi by L allowed values of k per 2 pi by L. Similarly, in 2 dimension, the allowed values of k is 2 pi by L whole square area, right? In 3 dimension, it is 2 pi by L whole cube volume, right? So this is a difference. Okay, so if you know in 1 dimension, you can extend the same idea to higher dimensions. Okay, that's what. So these are the 3-dimensional density of states. Means density of states in different 1 dimension, 2 dimension, and 3 dimension. And this is a very standard one. You can okay. There will be many questions like what is the density of states in 2 dimension? Okay, density of states in 2 dimension corresponds to the area, right? So it should be number of allowed k values are 2 pi by L whole square for 2 dimension, right? Similarly, for 3 dimension, it is 2 pi by L. Number of allowed values of k is 2 pi by L whole cube, right? So that, So, okay, this is a very basic concept. Maybe, okay, based on that, many questions might be asked like in different exams. Okay, so you should just keep this in mind. This is a basic simple concept. In one dimension, it is length, right? So number of allowed values of k is depends on the length, so which is 2 pi by L. Okay, in same in two dimension, it is area. Okay, two dimension area x y area. Area of a circle. So number of allowed values of k is 2 pi by L whole square. Right? And same in three dimension, okay, it's a volume of a sphere. So it is number of allowed values of k per 2 pi by L whole cube. Right? So this one you should, if you remember this concept, okay, any problems based on this one can be answered. Right? So number of allowed values means the density of states has been calculated, right? For different one dimension, two dimension, based on Debye's proposal. Okay, so you can apply this different boundary conditions, right? Okay, this is for three-dimensional volume. V by means L by 2 pi whole cube, right? Which is V by 8 pi cube. L cube is the volume, right? So now we have to calculate what is the different number of modes, okay, because the n omega d omega we want, because we have to substitute in the specific heat equation, right? So we can use this integration for volume, right? You can use instead of surface area into dk is the volume dv, right? D cube k is the volume. So you can use the differentiation here and substitute that in the okay, so this is n omega, you can calculate from here and substitute this in the CV, right? So the dispersion relation you can give this one. You can substitute that n omega value, n omega d omega value here, right? This is a Debye's equation for CV for finding the specific heat, right? Integration over 0 to omega maximum. So n omega d omega gives you the density of states, right, in a given solid system, whether it's one dimension, two dimension, or three dimension. So you can substitute that here, and the CE is whatever Einstein has used, right? These are Einstein's constant values, so you can put that here, substitute it here, and find the CV, right? So if you find the n omega here is calculated, okay, and substitute it here. So you can n omega, it will be coming around like this. So you can substitute that in this one. Okay, we can get omega maximum, okay, which is called Debye cutoff frequency, right? You might have heard about you can find the omega maximum, okay, which is a Debye maximum frequency available in that particular solid system, right? Whether one dimension, two dimension, or three dimension, right? So, okay, this is a problem given in basic any solid state physics book, right? From here, if you know n omega for different dimensions, you can put that in that equation and find CV. Okay, so this is what is the CV calculation will give you. Okay, which is theta d is the Debye temperature, right? Which just like Einstein temperature, which is called Debye temperature, right? And you can find, okay, this is a constant for a given solid, right? And you can evaluate CV of T, CV as a function of temperature from here, and it agrees very well with the experiment. Okay, as you can see, both at high temperatures and low temperatures perfectly matches with the theory as well as the experiment. Okay, so that is what is the so better agreement than Einstein model at low T, as you can see here, perfectly matching with the experiment, right? And for different elements and compounds, it's perfectly matching, right? And the Debye temperature for different solids are given here, and that's so. Even though it's a classical theory, right? Debye at 1912, he has not used any quantum mechanics, right? Classically, he has considered and derived in a methodical manner for what is the density of states. Okay, that his biggest contribution is density of states. Okay, so using just classical statistical mechanics, he has calculated the density of states, okay, in different one-dimensional, two-dimensional, and three-dimensional systems, right? And find a value for a specific heat for different solids, which matches perfectly with the experiment. Okay, so in general, the Debye temperature is related to the stiffness of the solid, how much the solid can expand, stiffness of the solid when you heat it, right? So okay, that is as expected. That's a physical meaning of Debye temperature. And so as you can see, as a function of T cube, if you plot the specific heat, it exactly matches from low temperature to high temperatures. Okay, so okay, this is what I want to say today. Okay, I think yeah, my time is almost up. Okay, so is there? Am I too fast, or I don't know? You can, if you have any queries, you can ask now. Okay, am I audible?
Yes, sir. You are audible, sir.
So I'm finished. I'm done with Debye theory matches with the experimental data, right? So Debye improved Einstein's model and find a very good relation for a specific heat of different solids. Okay, so both the theory and the experiment matches. Okay, and that's what I think. I will stop here, and if there are any queries, I can answer.
Okay, sir. I'll check for the queries on YouTube as well.
Please.
Sir, one of the student has asked that heat and temperature, how to differentiate between heat and temperature.
Heat and temperature. Okay. Okay. In terms of what? Okay, it's a very, very, very general question. Okay. How do you differentiate heat and temperature? Okay. Heat, which is what you feel. Temperature is a measure of the heat. Okay. So, okay, both are interrelated. Okay. Temperature is a measure of heat, right? So, okay, that much only I can say. Okay, there are, as you can see, there are different ways of measuring temperature, but heat is only temperature can be measured, right? Temperature is a measure of heat, that much I can say, right? So, any other queries?
Sir, I'm checking on YouTube.
Yes, please.
Dr. Senthil?
Yes.
So thank you so much.
Thank you.
There doesn't seem to be many questions.
Wow.
So
there are no questions on YouTube.
Dr. Savita, just check the YouTube also.
I've checked, ma'am.
Acha. Okay, fine. So that means either everything was crystal clear or everything went above the head, isn't it? So I think it was crystal clear, and that is why it was there was no need to ask further questions. So I think it was very nice. Thank you so much, sir.
I have sent you the PDF files, right?
Yes, and they are going to be sent to the students.
Okay.
Just now, today evening itself.
Yeah, sure.
Thank you so much, sir. It was indeed a pleasure for all of us, and will remain a pleasure for several years.
Sure.
Now, next, when you have students who don't understand basics, you can say, now you can refer to my YouTube videos, revise, and come again to the class.
Okay.
And save your save your throat from
Yes.
exercise again and again. Thank you very much,
Okay,
sir.
thank
It was indeed a pleasure. Okay,
Thank
so Dr. Savita, the next speaker, Professor Anirban, has already joined. Can you please make him co-host?
Yes, ma'am, I'm making it. I'm stopping the recording here once.
Students on YouTube, please join again on the NASI Delhi chapter channel of YouTube.